Alright, so we'll now discuss about kinetic measurements, or how we can measure experimentally the reaction rates. Again, by reaction rates we mean here the rates of composite reactions. Now the first method we will be discussing is titration based method. So maybe some of you have already done it in practical courses. So let's take a typical example. For example, say we can actually discuss about acid catalyst or base catalyzed hydrolysis of esters, where actually this ester bond is broken, or in one water molecule is inserted, and the reaction is overall that you get back your acid and the alcohol. Now this reaction is an example of bimolecular reaction, because you can see that the rate determining step the two species will be involved, but usually the water is present in large excess. So what happens is that the observed rate that you find is proportional to concentration of ester times the concentration of water. But since the concentration of water is too large compared to the concentration of ester, is practically it behaves as if it's a first order reaction. So this type of reactions we call as a pseudo first order reaction. Now when we do this experiment in lab, what we do is that in order to give some activation energy of the reaction, particularly for the base catalyzed reaction, you mix the ester and acid or base together, and the medium is of course water, and this water is present in large excess, and you put everything together and then you heat the solution mixture so that the reaction actually reaches an optimum rate. Now your T equal to 0 here is as soon as you mix it, but there is some physical error always involved, and in this case it is not much, because the kinetics of the reaction is very slow. The rate constant will be on the order of minutes. So whatever error we made is perfectly fine for this reaction, but we will discuss of course then the question arises that what will be the mixing procedure for reactions which are even more faster. So that we will discuss in the subsequent slides. Now first let us try to understand how do you analyze this reaction kinetics. Now as soon as you mix it and you heat it up, the ester actually produces acid, and this acid you can actually titrate. So what you can do, you can actually take the amount of the mixture at some regular interval. Suppose we take it at close to some 0 time. So T equal to 0, then we take again the mixture, say after 10 minutes, something like that. Then you again take the mixture after say 20 minutes, something like that, and then you take an equal volume of the mixture. So if I have the equal volume, since the concentration is changing, so the amount will also change, and if you titrate this same volume, you will see the amount of acid is actually increasing, which you can convert into the concentration of the acids, how it is increasing. Now one interesting observation or one crucial point here is that the moment you take this out, suppose after 10 minutes I take out this mixture, again the same volume of the mixture. Now within this reaction mixture, the reaction will still proceed, meaning your titration takes some time to perform, but you don't want the reaction to happen during that during the period of titration. So what you want is that you want a reaction mixture after 10 minutes, and immediately you want to stop it, you want to stop the reaction. So this is known as generally you want to basically quench the reaction. So the question is how we can quench the reaction in this case. Now this is very easy for this case. So what you do is that you take out the same volume and then you dilute it. You actually pour it in some excess water, so that the reaction mixture become extremely dilute, so that now the ester molecules and acid molecules are far apart, so the reaction probability will be less because of collision induced reaction. Also, what you do this reaction in an ice bath so that your temperature goes down, and as you know that every reaction needs an activation energy. So if I lower down the temperature, the reaction kinetics, I mean there will be less probability of crossing the activation barrier, so the kinetics will be much slower. So in general, you do two types of quenching here. One is basically concentration quenching, because you diluted the reaction mixture, and secondly you also did a temperature quenching. So you cool down the temperature so that you can arrest the reaction. So after 10 minutes if you do it, if you arrest the reaction, so you can approximate that whatever volume you are titrating, whatever volume of acid you are getting, and you can get back to the concentration, that corresponds to the amount of acid or the concentration of acid after 10 minutes of the progress. Similarly, after 20 minutes also the story will be the same. And by quenching, you made sure that the reaction itself did not proceed during your measurement. Now, as we just said, that this mixing, the time equal to 0 happens, I mean ideally, as soon as you mix all the reactants together. Now, in this case, again, the rate constant will be on the order of few tens of minutes or so, but in many cases, you do not have this kind of luxury, because as soon as you mix, the reaction actually proceeds. Now, with this method, you can get roughly up to say 1 minute or few tenths of second to 1 minute kind of resolution in your experiment. But we have most of the reactions are much more faster than this particular example. So for this, there are two methods which are developed. These are usually called as flow methods. Now we have two varieties of the flow method. One is known as a continuous flow method, and the other one is known as a stopped flow method. Now what is done in a continuous flow method? Suppose I am doing a reaction where the reactants are A and B, and I want to mix them and some product is being formed, let's say product P. Now what is shown in the upper figure is that A and B are initially kept in a vessel, and then there is a syringe, as you can see here. So we put a force on these syringes so that the reactants actually come and they mix inside a mixing chamber, which is shown here as M, and then this mixture actually continuously flow along this tube and ultimately gets collected in this vessel. Now what is going to happen here, as you can see right here, the reaction mixtures actually got mixed at a very early time, and then since they are flowing, if I measure something here, the product concentration, then that distance is directly connected to the time interval, because they got mixed and then they had flown along the tube. So if I measure at different position of say product concentration, so I will get actually the concentration of the product at different time. So if I am close to the right at the mixing chamber, which is denoted here as M, I will get a very early product concentration, and if I go far away, I will get a very product concentration at a later time. So the experiment will be something like, let's say I have a tube here, and then I can actually do a photometric experiment, something like I can have a UV lamp, and then I can have a detector here, and then you can simply study the absorption, and you can actually look at a characteristic absorption of the product. You can also study the characteristic absorption of one of the reactants. So if you follow the reactant, that absorption will keep on decreasing with respect to time. If you follow the product, absorption band will increase with respect to time. And from that, now you can actually, from the intensity of absorption, for products it is increasing, or for reactants it is diminishing. You can back calculate how much how much it gets converted into the concentration change, and from that you can calculate the kinetics. Now the problem with this flow method is that in this method again is known as continuous flow method, and the problem here is that you need a very large amount of sample, because the sample, as you can see, is ultimately wasted. The mixture is being collected in a vessel. Now in many cases you do not have that luxury. So if suppose you are working with a very small, particularly for biological samples, suppose you are working with an enzyme, and you want to study this enzyme substrate kinetics, how it is giving rise to the product. Now the question is how in these cases you will do these experiments. Usually, typically for enzyme catalyzed reaction, the amount you deal with is something like 100 microliter or even less. So it is less than 1 milliliter. Now the way is actually known as the stopped flow method, which is a modified version of the continuous flow method. So what is done here, as you can see here, that I have the similar mixing chamber like before, and then the solutions actually come here, they mix here, and then they start flowing, and then they are actually collected in a receiving syringe. And what happens is that you can see here, if I just put a force here, I am actually mixing A and B. So A and B are actually coming in the mixing chamber, and the mixer is flowing along the tube, and then it comes to the receiving chamber. Now the receiving chamber also has a syringe, and as a result, since I am putting a force here, this flow will cause this syringe to move in the other direction, and there is a circuitry. Once it actually reaches and touches this switch, then as a back reaction, as a feedback, this force will get stopped. So you force from one side, and the volume of the reactants move along the tube, and as a result the product is also being formed. And as soon as the volume gets transferred substantial amount in the receiving chamber, the receiving chamber syringe expands in the right hand direction, and then it stops the circuitry. So what will happen as a result, that if you now look at the situation after the flow has stopped, then you can think that if I fix my spectrophotometer at a particular position and then take the spectrum over time, then the flow actually has stopped everywhere. So what we do here is that we mix the thing, and then in the earlier case, the difference is that in the earlier case it was continuously flowing, and then I was saying that at a different locations I have different locations basically maps into different time intervals. But in this case I have mixed and immediately I have stopped. So stopping means now I have a mixed solution along the tube. So I can actually choose one particular location along the tube and then take my data over some interval of time. So the difference here is that I'll put the same thing, lamp and the detector, but this time I'll fix the position, I'll not change the position. Earlier time I have to actually scan the lamp and the detector together along this tube, so that I can get a temporal information for spatial location. Here the flow has stopped, the mixing is completely done after a certain time, as soon as the circuit is off, and automatically in a feedback electronic circuitry the flow is stopped, and then you start your measuring, and then you say that I can actually sit a particular region in space and then keep on detecting over time. So in a sense, the stopped flow technique is a static technique. You started the flow, you mixed it, but immediately you stopped the flow, and now you look at a particular region in space over time. So you are getting a direct temporal information and you do a direct time domain experiment. But in the earlier case, you continuously make it flow, and then you make sure that your flow is converted to your time. The only precaution for these methods is that, particularly for the continuous flow method, that your velocity and should be very uniform. Otherwise you cannot calculate the amount of volume. If the velocity has huge turbulence inside it, you cannot actually easily map the concentration over time to distance. And in the stopped flow technique, those are kind of eliminated. But again, each method has its own limitation. Like in the stopped flow, you have to make sure that the flow stops very quickly. So the way it is drawn here, in reality actually this volume of the mixing chamber as well as the receiving syringe is much smaller, because as I said that you only deal with something like, say, a few hundreds of microliters of the reaction volume. So this is these kind of experiments which I said, the earlier one like the titration based experiments, for slower kinetics, and these continuous flow and stopped flow kind of experiments are routinely done. And in the earlier case, I said that it gives you about a few tenths of second to 1 minute resolution. And in this case, stopped flow, you can get down to something like 1 millisecond resolution, 1 millisecond to 1 second. But usually, chemical reactions are extremely fast, and most of the chemical reactions. And as soon as you mix, it just starts. Now, the question is how one would handle this problem, or how one wants to deal with this problem. Now, this problem has a very good analogy with developments in other areas that I'll give you an overview. Now, this is known as our race against time. So, over time, the human race has struggled continuously to find better and better time resolution so that they can capture events which are faster. For example, there was a very classic experiment where it was asked, or it was basically speculated, when a horse runs, what happens, what is the motion of the horse. And this experiment was done in way back in 1872 or so. He was a journalist, Edward Muybridge, and he was asked by the mayor in San Francisco that just make sure, do an experiment which actually proves when a horse actually runs, whether you get a situation or you get a moment at which all the four legs of the horse is in the air, or it is something like that the horse always touches the ground with at least one of its foot. Now, this is a very complicated problem for that, if you think that it was 1872. And then Muybridge actually did a very, very tedious experiment. So, what he did is that he he actually brought a series of cameras, and each camera, I mean, there was no video camera available that time, and he placed those cameras at a regular interval in space on the track, and then he made all these cameras in a synchronized fashion, meaning one camera will take the snapshot, and say after 1/10 of a second, the second camera will take the snapshot, something like that. And what he did is that after a lot of trial and error method, he basically collected a series of pictures of the horse. Now you can see here that this is the first frame, this is the second frame, something like that. And interestingly, you notice this frame where actually all four legs are in the air. So when Edward Muybridge did all this collection of the frames, and then what he did is that he projected it onto a white screen, and he basically made a device. He was basically rolling the films and while projecting, and if you do it very fast, you will see the horse in motion, and that's exactly what he could produce. And this is one of the first example of video microscopy, but this is not a direct video microscopy. Remember that this was basically many synchronized static frames, but with this he made it possible to visualize that actually during its motion the four legs come into air at some instant. Now, with this thing, you can get something like which you cannot see. I mean, there is a word like a blink of the eye. So, what you cannot see with the blink of the eye, that you can visualize, but that means actually it is something like a millisecond resolution or so. And then came another era where actually people talked about stroboscopy. Now, what is stroboscopy? Now, in the earlier case, you see that how do you see an object? You basically throw light on it, and then the light reflects from that object, goes into your eye or the detector, which is the camera in this case, and it captures the frame. Now, you take multiple frames, but the event which you are, the way you are detecting is actually continuous, because light is continuously falling on the object and it's continuously coming to your eye. Now, stroboscopy has a very different idea. Stroboscopy tells that what happens, instead of sending light continuously, if I actually send light as a flash. Now, you have seen flash lamp, like in camera flash lamp, so which has on the order of say few microseconds to 100 microseconds long. So, if you send a flash to the on the object, then the object will be illuminated only for a very short time, and then the reflection from the object or the scattering will also come for a short time, and then you can actually capture. So, then you do not need a camera with a very high shutter speed, you can actually have a continuous camera, but since your light exposure is short, your events you capture is only on the order of very short period. Now, this idea was put forward by an American engineer, Harold Edgerton, and this is basically the setup. As you can see, in those days there were big flash lamps which are available, and these are basically the capacitors of the flash lamps, and you just basically charge the capacitor and then immediately you discharge it, and then you get a microsecond flash. And these are basically the concentrators which you have seen in photographic studios, which actually focuses the light. Now, with this kind of flash experiments, Edgerton was able to collect extremely good images which are otherwise aesthetically very beautiful. Now, you can see here, this is a moment when a bullet pierces through a card. This is a moment when the bullet actually pierces through an apple. And this is a picture what happens when a milk drop actually falls on a surface which is red colored. So it creates a very beautiful pattern. Now, the same idea of this flash lamp photography was actually picked up by chemists, and then basically they started something which is known as flash photolysis. Now, what they said is that the three gentlemen, Manfred Eigen, Ronald Norris and George Porter, they said that I will initiate a reaction with a very short burst of light, which I call as a flash, and in this case it is the same flash, it is a microsecond or a few tenths of microsecond long flash, and then what I will do, I will just see the formation of the product. Now, you can connect it to the earlier discussion of the mixing. As I said, that A and B are mixed together, and that mixing has to happen very quickly, because if the entire reaction happens during the course of mixing, then the stopped flow or the flow method doesn't work at all. So, their point was that you can actually study with this method what is known as photochemical reactions that are triggered by light. Now, this triggering, I am not actually doing it by continuous light, because if I continuously expose light, the reactions will be over during the exposure of the light. So, I want to initiate the reaction with a very short pulse of light, meaning this short pulse or short burst of light is so short that I can think that the reaction does not proceed within the duration of the flash. It just initiates the thing, and then subsequently you observe the product. So, we have a setup, schematic of a setup here, and we have a better picture in the next slide. All this, wherever I have adapted the pictures, I have given the references at the bottom. So, you can go back and have a look at these references. Now, what is shown here is that there is a flash lamp here, as you can see, and it has a capacitor. As I said, that the capacitor has to be charged first. Any flash lamp is nothing but a discharge tube. So, you have a rarefied gas in a vacuum tube, and then make a short circuit, you just make a connection of this open circuit. Then you have a discharge inside that tube, and depending on the amount of the gas and pressure of the gas, and of course the nature of the gas, you can actually generate a flash of a very short duration and of a particular wavelength. And that light which is coming, that actually initiates the reaction. And the reactions are already kept in the vessel, but the reaction does not happen all of a sudden, because it needs a photon to initiate the reaction. So, the flash actually initiates the reaction, and as soon as you initiate, suppose I had already mixed A and B together, and it gives me product in the presence of light. And as soon as I give this light in the form of a, say, microsecond flash, it is something like, say, on the order of, say, 10 microsecond, the reaction initiates and the product P forms. Now, again, everything has a time scale. The product P will form over time, and then what I can do is that I can actually simultaneously pass a light beam and do some absorption or emission based experiment, as I just outlined in the previous flow technique. And then one can see directly in the oscilloscope or in some detector how the product actually gets formed. So, suppose this is the time at which I started my flash, and then all of a sudden I will see that the product concentration will rise, and then it will reach at an equilibrium. So, from that time scale I can actually calculate what is the time scale of formation of the product, something like that. So you can also see the other picture. So at this point, as you can see, the flash was initiated. This is my time 0, and then the absorbance of the product actually increases and it reaches to the maximum value, and from the growth of the slope of this curve you can actually find out the kinetics. Now again, this method has its own limitation because it depends on what is the width of your flash lamp. Now usually you can go with this flash photolysis technique down to 1 microsecond or so. Now eventually what Norrish and Potter developed, instead of using a flash lamp flash photolysis, they actually improved it to something known as laser flash photolysis. So instead of a capacitor based microsecond flash, they actually used a laser pulse to photolyze this experiment, and where you can actually use a laser pulse of a few tens of nanosecond duration, something like that. So with this technique they were able to detect events which are much shorter, something like 10 nanoseconds or 100 nanoseconds or so, and that's why when these gentlemen were given the Nobel Prize in Chemistry in 1967, the citation says for their studies on extremely fast chemical reactions that were not possible to study with flow techniques or stopped flow techniques. And also you see that they are writing here, they are affected by disturbing the equilibrium by means of a very short pulse of energy. Now this energy they showed eventually it can be an electronic pulse also, like if you have an electron transfer reaction you can think of it, I'll trigger it with some flash, not a light flash but with a electrical flash, something like you can actually send a bunch of electrons with an electron gun, something like that. But another point to look at here very carefully, it says that the effect by disturbing the equilibrium, this is very, very important. So what is happening here is that we already discussed what happens if I have a reaction, something like that A is going to B and B is also giving back you the reactant, and then you showed that in a very long time limit both an A and B are actually reaches that equilibrium value. A doesn't go to 0 because it always reaches its equilibrium value because it's a reversible reaction. So the overall idea in flash photolysis type of experiments is that you all of a sudden you had a mixture and all of a sudden you disturb that mixture. Initially A and B suppose were in a thermodynamic equilibrium, and all of a sudden you start the reaction to proceed. So you are disturbing the equilibrium and you are basically moving this entire mixture from equilibrium to far from equilibrium, and then slowly again the product forms and it comes and establishes a new equilibrium. So that's why you see a kind of growth in the product, and you can think that initially I had an equilibrium of the only between the reactants, and then of course they are not reacting, they are just thermodynamic equilibrium, and then all of a sudden you make them react because now you are disturbing this entire system and you are pushing it far from the equilibrium, and then you are seeing that how basically the product is formed. Now this general concept is known as relaxation methods. So by relaxation method you mean that you start with a mixture and then you create some disturbance where the entire mixture actually goes far from the equilibrium position, and then it relaxes back to the equilibrium. And something like say for example you can also, instead of doing a electronic flash or say photo flash, you could also do a temperature flash, something like you can actually send a huge change in a heat pulse so that the temperature actually changes all of a sudden, and then your reaction initiates, and then again the system thermally equilibrates and goes back to the a new equilibrium. In this case always you have to remember that it doesn't go back to the old equilibrium because a reaction is happening, so it gives you the product back. But the overall idea is that there was an equilibrium, you disturb it and then you establish a new equilibrium, and you watch over time how this new equilibrium is established. So as is shown here, that the product goes, or product basically accumulates over time, and that's a new equilibrium where you have predominantly product in the mixture. So again, these are collectively known as relaxation methods, and we have many different methods like temperature jump experiments, flash photolysis, all fall under these relaxation methods.